Welcome to the first example of our series parallel circuits. This is a part of our DC circuit fundamentals course. The students are expected to have the skills to analyze the circuit in their final exam. So I am going to post a few videos, and this is the first one with the first example. In this circuit, you can see that there are three resistors. Some of them are in series, some of them are in parallel, and the task of a student will be to first simplify the circuit and then to analyze the circuit. Let's have a closer look at each task. So to simplify the circuit, what you're actually trying to do is you are trying to go from a circuit that has many components in it to a circuit that has one resistor, one power supply, which will enable you to calculate the total current. So the simplification of a circuit should always end up with the simplest form of an electrical circuit, where you have a power supply, you have a load, which in this case we're going to call R total, and that will allow you to calculate I total. All right, to analyze a circuit, you're going to make sure that you have calculated each and every value of current. You see there are three currents because there are three resistors, and voltages. You see there are three voltage drops because there are three resistors. And once you have done all that, you'd be able to say, I've analyzed the circuit. Now I know all the values that are in the circuit when it is operating. You can also say that I can calculate the rating of the power supply, the wattage of the power supply, because I have the voltage supply and I have the I total in this case. So in doing the two steps properly, you will end up with analyzing the circuit. And this is, I would say, the most simple version of a series parallel circuit, in which you have both currents that are resistors that are in series and resistors that are in parallel. Now, to simplify a circuit, you're going to do 1, 2, 3, 4 steps. First of all, you're going to identify the nodes in the circuit. That is going to lead you to identify the resistors that are in series and the resistors that are in parallel. And you're going to keep repeating the second and third steps until there is only one resistor left in your circuit. All right, so let's start with identifying the nodes here. When we identify the nodes, I usually color code the node. So you have a node here. A node, if you remember, is any stretch of wire or wires through which there is no voltage drop. The current passes through this node at any point of it without experiencing resistance. Practically, there's always some resistance, but practically you can say that the resistance value in this piece of wire, for example, is negligible. And then we have a second node here, and then finally a third node here. So this circuit has three nodes in it. And how do we go and identify now series and parallel resistors? I'm going to go over the two rules that make you identify series and parallel. The first one is in series. Two resistors in a loop, basically. In a loop, two resistors are in series if the current passing through one, so this guy here, let's say the current passing through here, is also passing in its entirety, this is the key word, in its entirety, through the other resistor. So let's have a look here. We know that the current is going in this direction, and then the current is going in this direction, and then the current is going in this direction. This is supposed to be, second nature to you by now to decide the direction of the current. It's going like this. Now, we have I1 and we have I2, right? So I1 is going like this, I2 is going like this. So the same current is going through R1, and it's also going through R2. Are now these two resistors in series? Well, the answer is no, because the current that is passing through R1, it's not passing in its entirety through R2. We know this because when the current I1 comes into this fork in the road, it has to be distributed, it has to be divided between R2 and R3. So basically R1 is not in series with R2, and with the same logic and reasoning, R1 is not in series with R3. How about parallel? Well, okay, two resistors are in parallel if they're ends on one side. So let's just very quickly have a look at ends on one side. So you know that each resistor has, two ends like that. Each resistor has two ends like that, as you can see. Or even you can say, for example, I'm going to use another color here. This is an end, this is another end here. So each resistor has two ends, right? So the rule is that if, two resistors are in parallel if their ends on one side are connected to one node and their opposite ends are connected to another node. I can see that R2 and R3 are in parallel, so let me explain how I apply this rule here. I'm going to use this end here and this end here of R2 and R3. They are on one side of the two resistors and also connected to the orange node. So they are connected in one node on one side. And also the other end, the opposite end of each resistor is connected to a different end. Okay, so this has been fulfilled now. This rule has been fulfilled now. Therefore, R2 and R3 are in parallel. Okay, so you can repeat doing that as long as you want until you get to a single resistor. Now, if I have determined that R2 and R3 are in parallel, I can use either this formula or I can use this formula to calculate their equivalent, R equivalent 2 and 3. Okay, I like this formula. It's just simpler when you look at it, and it's also easier when you're using a calculator. A lot of people actually are very good in using the calculator to do this, and the advantage of using this format of the formula is because you can add so many other resistors. If you have 4, 5, 6 resistors in parallel, you can just add them, plus 1 over R4, for example, plus 1 over R5, and so forth. You can go forever. But this is only for 2 resistors. I'm going to stick with this one here. I just basically like it more. It's simpler. So now I will take the values R2 and just plug in R3, plug in the formula here. So if I do that, I get 15 times 30 over 15 plus 30, which is 450 plus 4 divided by 45, and that makes the R equivalent for 2 and 3 equal to 10 ohms. What I would do is I would just literally erase R2, erase R3, and then replace them with their equivalent, R equivalent 2 and 3. Now it becomes obvious that R1 and R equivalent 2 and 3 are in series. Why? Because the previous rule we talked about, you know that the current passing through R1 is also passing in its entirety through R equivalent 2 and 3. And if that's the case, then R total, I know that the equivalent of those two is going to be R total because there is no other resistor left in the diagram. So R total is equal to R1 plus R equal 2 and 3. That's 10 ohms. We have seen that this is equal to 10 ohms, and the R equivalent we just calculated to be 10 ohms. So their equivalent are going to be equal to 20 ohms. What we have done is we have finished successfully simplifying the circuit. Now we have a circuit in which we have one resistor, which is equal to 20 ohms, and we already know the power supply is 60 volts. Obviously now we can start our analysis. So the first rule, the first step of analysis is use Ohm's law to calculate total current. I am more than happy to do that. In this case, the Ohm's law is going to be voltage supply, which is 60, equals to the total current multiplied by the total resistance. This is 60 is equal to I total multiplied, R total is 20 ohms. So I total equals to 60 divided by 20, which is equal to 3 amps. There you go. Now you know that the current here is equal to 3 amps. The current that is passing through here is equal to 3 amps. Coincidentally, this I total here is also the same as I1. It's the same. So you can literally say I1 equals to 3 amps. That's the first step, and it's not a bad step. We have calculated two values with one stone, basically. Right. So after we have done this first step, we're going to move on and continue using Ohm's law, the current divider, voltage divider, Kirchhoff's voltage law, Kirchhoff's current law to calculate everything else, basically voltage drop and current in each branch. So as I have wrote in the previous slide, I1 equals to 3 amps. If I know R1 and I1, then what's stopping me from calculating V1? I can easily do that right now. So I1 is 3 amps multiplied by R1 is 10 amps. So V1 is going to be 30 volts. That's it. We have just calculated 30 volts. Congratulations. The first component there has been analyzed in its all values, basically resistance, current, and voltage. And by the way, when you know current and voltage, you can always calculate the wattage of the resistor. You can say this resistor requires 90 watts voltage multiplied by current, and 90 watts is that's quite high actually, but 90 watts is the rating of this resistor. Okay, so let's continue with the rest of the calculations. We still have to calculate basically I2, V2, I3, V3. I mean, that's 4 different calculations. How do we do that? You could use either current voltage dividers, or you could use Kirchhoff's law, does not matter. In my experience, what I would use is the current divider in this case, just because I can see that the current is coming into here and it's being divided into I2 and I3. So again, I1 is coming into a fork in the road and it's being divided into I2 and I3. All right, the current divider rule is right here. Okay. So what we're going to do is we're going to apply it. R3 is 30 volts, ohms, and that's going to be divided by 15, which is R2 plus 30, multiplied by I in. I in is the current coming into the fork here, which is, we just said it's 3 amps. So you have 90 divided by 45, which is equal to 2 amps. There you go. We have calculated I2 to be 2 amps. So the next thing is V2. We're going to use our beloved Ohm's law right here. V2 is equal to I2, we just calculated to be 2 ohms, multiplied by 15, which is given to us, which is 30 volts. So that's 30 volts. Now you could go and use the current divider to calculate I3. However, at a quick glance, if 3 amps are coming into here and 2 of them are going here, only 1 is left to go through R3. So you could say I3 is 1 amp, but for the practice purposes, I'm going to do the calculation anyway. So I3 equals to R2, which is 15 ohms divided by, again, 15 ohms plus 30 multiplied by the current coming in, which is 3 amps coming in. So 45 divided by 45, and it is indeed 1 amp, as anticipated. Of course, now using Ohm's law, it's going to be easy to calculate V3, which is 1 amps amperes multiplied by 30 ohms. That's giving us basically 30 volts. And obviously, this is 30 volts. And obviously, we should have known that because we said R2 and R3 are in parallel. Whenever you have two resistors in parallel, the voltage drop across the two should be equal. Whatever V2 is going to be V3 as well. So at this point, we have completed our analysis of this circuit. One more note for you guys that when you look at diagrams, you have to also remember that even though these four diagrams have different shapes, they look different, but they are the same electrical diagram. I mean, for the purposes of calculating the currents and the voltages and everything, they are identical diagrams. They all have three nodes, 1, 2, 3 here, 1, 2, 3 here, okay, 1, 2, and 3 here, and 1, 2, and 3 here. You see, they all have three nodes, but also between each two nodes, you have the same resistor. So for example, between node 1 and 2, you have resistor R1. Between node 1 and 2, you have resistor R1. Between node 1 and 2, and between nodes 1 and 2, you have R1. And if you continue between nodes 2 and 3, you're going to see that they are the same thing. Now, there is no reason for me right now to choose one or the other. I chose this representation just because it's visually easier. You could have chosen this. It's still easier. This might be even easier. It depends on the bigger picture, where you're going to put this circuit in the bigger picture. That's the only reason. So one more time, we have simplified the circuit. We have analyzed the circuit by calculating all the values. And now we're going to go to the next video where we're going to do the second example. And the examples are going to be progressively harder and harder. I mean, they're not really hard, but they're going to increase in complexity.